Good afternoon to all. I hope my screen is visible to all of you.
Yes, sir.
Yes, sir.
Yes, sir.
Thank you. Thank you very much. Okay. So in today's session, before going to today's session, we'll recap the last last class session. Okay. So in last class, we discussed about recursion. Okay. So whatever, if any repetitive process we need to implement means the repetitive problems can be solved using iteration or recursion. Iteration means using the iterative statements like for loop, while loop, do while loop. Or we can go for the recursion. Recursion means a function which calls itself. Okay, an algorithm which calls itself is called as a recursive algorithm or recursive function. Okay, using recursion also we can solve the given repetitive problems. Okay, so this is what recursion. Then we discussed about how to design recursive algorithm. We discussed about the rules also. There are two rules, basic three rules for the designing recursive algorithm. Okay, first is identifying the base case, the second one is identifying the general case, the third step is combining the base case and general case and completing the algorithm. So this is a basic rules for designing any recursive algorithm. Okay, and in today's session we will see two or three examples for the recursive algorithm. And before that, I wish to remind you one thing. As we already discussed, uh, the assessment for this course. Okay, so totally 8 assessments we are going to conduct. Two assessment for each unit. One assessment will be MCQ, and the other second assessment will be theory part. So theory part means there may be some questions related to algorithms, algorithm writing or program writing, or some descriptive questions. Okay, so each test carries 20 marks. Okay, from that best of 5 will be taken, and that mark will be converted to 25 marks. So as part of the assessments, next week you will have test for this first unit. Okay, so next week mostly on Friday, Saturday classes. Okay, Friday, Saturday classes you will have assessment for this first unit course. Now mostly we are at the end of the first unit. So for this first unit exams, assessments will be in the next week, Friday, Saturday classes. Any doubt regarding the assessments? Okay, so let us move to the today's content. Okay, so first recursive algorithm what we are going to discuss is a GCD, greatest common divisor. Okay, so the greatest common divisor between given two integers. Okay, how to find it? For that we are going to use Euclidean algorithm. Okay, so as the Euclidean algorithm definition is given here. If you want to find GCD of A comma B, suppose if B value is 0 means the GCD is A. If A is 0 means GCD is B. Otherwise, GCD of B comma A mod B. Okay, GCD of A mod B. This GCD of B comma A mod B, its GCD is equal to GCD of A comma B. So that is what the definition as per the Euclidean algorithm. Okay, so in the uh, below this definition I have given one URL, Khan Academy URL. Okay, so in this URL how this uh, steps, okay, there is a GCD calculation, it is clearly explained with the example. Okay, so you can go through that example. If you are unable to understand this definition, there is a GCD of A comma B equal to GCD of B comma A mod B. Okay, so this definition clearly explained in the Khan Academy URL, you can go through that. Now how to convert it into algorithm? Okay, so see here, this is the general definition given for the GCD. Okay, if B equal to 0 means A is the solution, and if A equal to 0 means B is the solution, and otherwise GCD of B comma A mod B. So this is the GCD for GCD of A comma B. See here, the same thing we are converting into algorithm, that is GCD of A comma B. If b equals to 0 means return a. If a equal to 0 means return b. Otherwise, return GCD of b comma a mod b. When the remainder becomes 0, that time b will be returned, and that b value is the GCD for a comma b. Okay, so how this will work? Okay, let us see the programming exam, means the program code implementation for this program. See here, the algorithm here we converted it into C code. Okay, so integer GCD. Okay, so we are passing two parameters a comma b, and then if b equal to 0, return a. If a equal to 0, return b. Return GCD of b comma a mod b. So this is the recursive version. Okay, recursive version of the algorithm. Okay, and below that we have given iterative version of the algorithm. Okay, iteratively the same Euclidean algorithm, how to convert it, implement it using the iteration. So that is also given here. So in whatever the problems we discussed so far in recursion, okay, we have given the recursive solution and also the iterative solution for your understanding purpose. So you can compare both. Okay, now we are calling both GCD1, it is a recursive version, and GCD2, it is a non-recursive iterative version. Okay, just 1 minute. So in both iterative version and recursive version, for the 10 and 25, GCD is 5. Okay, we are getting 5 as a result. Suppose if I am changing the first parameter as a 0. Okay, so let us only do it in the recursive version. Suppose if the first parameter is 0, then the GCD is 25. Okay, see here, it is 25. Suppose if the second parameter is 0, then the first parameter is the result. Okay, see here, we are getting 10 as a result. So this is the GCD program, greatest common divisor. Okay, this is a recursive solution for finding GCD. If you're looking at the steps, the statements that we used in this function, it is very simple. Suppose if somebody is asking you to write it in a for loop, the for loop or while loop statements, it will take more statements. The solution using the iteration, it may take more more steps, but the recursive version, it takes very less number of steps, and it is very simple. See here, if b equal to 0, return a. If a equal to 0, return b. So these 4 statements are also simple solution, and the last one, return GCD1 of b comma a mod b. That's it. This is the only major statement in this recursive solution. So compared to the iterative solution, if you are looking at the recursive solution, okay, it is very simple. That's why the recursive solutions are very simple to implement. But efficiency wise, it will take more memory space and time. So the problem that you are going to solve, if it is a simple problem and there is no issues about the memory and time, in such case you can go for the recursive solutions. Otherwise we need to go for the iterative solutions. So this is the recursive solution for the GCD problem. Now the second solution, okay, so the program is given in the slide itself. Okay, the second solution is the second example that what we are going to discuss is a Fibonacci series. So this program also you might have implemented in using for loop or while loop, in your first year courses, programming in C course and CPP course. So Fibonacci series, what is this Fibonacci series means? The sum of the first two digits is the third value. Okay, the previous two values is the current value. Okay, so this is what Fibonacci series is. So the first two digits in Fibonacci series is always 0 and 1. The third term, okay, first term, second term. The third term is the sum of first term on second term. That is 0 plus 1 is 1. Now sum of the fourth term is the sum of second term and third term. 1 plus 1, 2. The same way, how this 3 is coming? 1 plus 2 is 3. Then 5. 2 plus 3 is 5. Then 3 plus 5 is 8. 5 plus 8 is 13. So this is a Fibonacci series. How to generate this Fibonacci series? This is also a repetitive process, means repeatedly we are performing the addition operation of the previous two terms. So this problem can be solved using iteration and also recursion. Okay, so iterative solution and recursive solution, both we will the programs we will see. So before that, the recursive solution. Okay, so what is the design for design for the recursive solution, that we will see here. So here 0, if a number of terms is 0, then 0 is the result. If number of terms is 1, then 1 is the result. Okay, suppose otherwise, okay, if number of terms is 3, means its value is n minus 1 plus n minus 2. Okay, from current value, suppose if you want to calculate the third term, means okay, second term plus first term, that is what third term. Okay, so Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this is what the recursive definition for the Fibonacci series. Okay, now let us see the algorithm. So actually for this Fibonacci series, the algorithm is not given in the textbook. You can write your own algorithm. Okay, see here, let us take the Fibonacci of n. Okay, for Fibonacci of nth number, okay, how to find it means Fibonacci of n minus 1 plus Fibonacci of n minus 2. These two first we need to calculate. Now how to calculate Fibonacci of n minus 1? N minus 1 minus 1. So it is a Fibonacci of n minus 2, and a Fibonacci of n minus 1 minus 2, that is Fibonacci of n minus 3. Okay, sum of these two is Fibonacci of n minus 1. The same way, how to do it for n minus 2? Fibonacci of n minus 2 minus 1, that is n minus 3. Fibonacci of n minus 2 minus 2, that is n minus 4. So sum of these two is the Fibonacci of n minus 2. So this is how the recursive function calls will work. Suppose if you wish to calculate for Fibonacci of n 4, okay, so first we need to calculate for 3 and then 2, 1. Okay, and what is the 2? 2 minus 1 is a 1, 2 minus 2 is a 0. Okay, we know that Fibonacci of 1 value and 0 value, it is a 0 and 1. So 1 plus 0 is 1, that is what the value of Fibonacci of 2. Okay, now 1 plus 1, this is what the value of Fibonacci 3. Okay, 1 plus 1 is 2. 2 is the third term. See here, in this third term, okay, 0, 1, 2, 3. Third term is 2. Okay, third term is 2. Fibonacci of 3 is third term is 2. That is Fibonacci of 0th term is 0. Fibonacci of first term is 1. Fibonacci of second term is 0 plus 1. That is 1. 0, 1, 2. Second term, its result is 1. Okay, and then performing the addition operation, we will get Fibonacci of 3. Okay, so this is a illustration about the how the function call will work in the Fibonacci recursive implementation. Okay, see here, this is the implementation for finding the Fibonacci series. Okay, so this will not print the entire series. This function will calculate nth Fibonacci number. Okay, suppose if you want to print 10 Fibonacci numbers, 10 times we need to call this function. Okay, so this function will calculate the nth Fibonacci number. Okay, suppose if you want to print n numbers means n times we need to call this Fibonacci function. Okay, Fibonacci function. See here, from main we are calling 10 times this series. Okay, integer looper equal to 0, looper less than series size, looper plus plus, printf Fibonacci of looper. So first time the looper value is 0, so Fibonacci of 0. So 0 will come to num. Since num is 0, it will return num. So we will print 0 as the first number. See here, in the result you can find 0. Then the loop will be incremented. Looper will become 1, Fibonacci of 1. So Fibonacci of 1 means num value is a 1. Since num value is a 1, it returns 1. Okay, so 1 will be printed and the second term is a 1. Now the looper will be incremented. Now looper value is a 2. So Fibonacci of 2. Fibonacci of 2 means num value is a 2 and the num value is not 0 or not 1. So it will go to the this recursive function call. Okay, Fibonacci of 2 minus 1, that is Fibonacci of 1, and Fibonacci of 2 minus 2, Fibonacci of 0, Fibonacci of 1 and Fibonacci of 0. Two function calls. Okay, Fibonacci of 1 value it will return 1, and Fibonacci of 0 value it will also return 0. So 0 plus 1 is 1. That 1 will be printed here. Okay, so this is here in this function, in recursive function call, we are calling the function 2 times. Within fib we are calling fib of n minus 1 and also we are calling fib of n minus 2. Okay, so this is the program to calculate the nth Fibonacci number. Okay, nth Fibonacci term, and the result is given here, Fibonacci series. Okay, let us check the implementation also. Fibonacci series. See here, for this program also Fibonacci series we have given recursive output and also iterative output. Okay, recursive implementation and iterative implementation. So this is a recursive implementation and this is iterative implementation. Okay, fib2 it will print n terms. Okay, for this I am passing n, means this iterative implementation we are printing the entire series. In the recursive implementation we are calculating the nth term and calling this function n times from the for loop. Okay, so for fib2 I am passing 10 and fib1, okay, recursive function, it will be executed for 10 times. Okay, let us check it. See here, both recursive solution and iterative solution both giving the same result. Okay, now how to calculate the nth Fibonacci term, how many times the function call will be executed? Okay, how many times the function call will be executed? See here, if you want to calculate Fibonacci of 1, the number of function calls is 1. From main it is going to the function and immediately it returns 1. Okay, to execute Fibonacci of 2, this second term, totally 3 calls are executed. Okay, so 2 will go to the function, and since 2 is not equal to 0 and not equal to 1, it will invoke 2 function calls. So there is a fib of 2 minus 1 plus fib of 2 minus 2. That is fib of 1 plus fib of 0. Okay, those are 2 calls, and from main function 1 call is happening. So totally 3 function calls. Just to calculate the second term in the Fibonacci series, we need 3 function calls. Okay, so if you are increasing the number of number of terms in the Fibonacci series, the number of calls is okay, it is exponentially increasing. Okay, for 5th term, if you want to calculate 5th term, totally 15 function calls are required. For 10th term, okay, see here 177 function calls are required. Okay, And for the 40th term, see here how many number of function calls are required. Okay, so printing Fibonacci series using recursive function call. Okay, recursive implementation. Okay, it is very less efficient compared to the its equivalent iterative solution. Okay, now the third example that we are going to discuss is Towers of Hanoi. Okay, this program also you might have implemented in your programming in C course. So before enter into this Towers of Hanoi, so just a brief introduction. So what is this is based on some story. Okay, so what is the story here means? Okay, somewhere in the world, okay, some place, one old monk, okay, he is transferring some gold disc from one needle to another needle. Okay, there are 3 needles available. Okay, and in one needle, totally 64 golden discs are there. Okay, so he has to move one disc at a time from source needle to designation needle. Okay, he has to move one disc per hour. Okay, for each hour he should move only one disc. Okay, based on this, once he moved all the 64 discs from the first, that is the source needle to designation needle, then that is the end of this world. Like that, some stories are there. Okay, so based on the story, this problem is developed. Okay, so here what is our objective is we have to move the disk. Okay, so here we have 3 needles, source, auxiliary and designation. We have to move all these 3 disks from source needle to designation needle in the same order. Okay, means the bottom must be the larger disk and the top must be the smaller disk. Okay, and at any point of time we have to move only one disk. Okay, we have to move only one disk. We cannot take all the 3 disks and keep it in designation. Okay, we have to move only one disk at a time. Okay, and the second condition is at any point of time there should not be a larger disk on a smaller disk. Always smaller disk must be over the larger disk. Okay, you should not keep a larger disk on a smaller disk. So these are all the conditions. Based on this condition, to move these 3 disks to designation, how many movements we need to make? That is what the question here. How many movements we need to make means it is 2 power n minus 1. Okay, here n is the number of disks. Okay, here totally 3 disks are there. So 2 power 3 is 8. 8 minus 1 is 7. So minimum 7 movements we need to do to move all these 3 disks from source needle to designation needle. Okay, so calculating this is a Towers of Hanoi problem. Suppose if you are trying to solve it using iteration means, okay, it is very difficult to implement. But using recursion, we can implement very easily. The solution will take only 3 or 4 lines of code. Okay, so that is what the advantage of recursion. Okay, the solution is very simple to implement, but its efficiency is less. Okay, now let us go to the algorithm implementation for this Towers of Hanoi. Okay, so let us solve this problem from smaller perspective to larger perspective. Means let us solve it from one disk. Suppose if you wish to move one disk, if we have only one disk, means we can directly move it from source to designation. Okay, now second case, let us take, assume that we have 2 disks. So if we have 2 disks means what we'll do, we will move the smaller disk, okay, from the source needle to the auxiliary needle, that is B. Now the second disk, assume that we have only 2 disks. The first one is, that is the topmost is 1 and the bottom is a second disk. So move the first disk to the auxiliary needle B, then move the largest disk, second disk, to the designation node C, then move the smallest disk which is already available in the B, auxiliary needle, to the source needle. Okay, so this is what the step we will do it. Okay, so basically here what we are doing means first we are moving n minus 1 disk. Okay, here n value is 2. Okay, so we are moving n minus 1 disk to axillary needle. Then we are moving the nth disk from source to destination. After that, again we are moving n minus 1 disk from axillary needle to destination needle. Okay, so this is what, these are all the 3 steps mostly we are doing. That is, move n minus 1 disk from source to axillary, move nth disk from source to source to destination, and finally move n minus 1 disk which we already moved to axillary. Okay, that move to the destination. Okay, so these are all the 3 major steps we are going to implement. Okay, now if we have 3 disk, okay, see here, move 2 disk from source to axillary. Okay, totally 3 disk, so n minus 1 is 2. Okay, so move 2 disk from source to axillary, then move the first disk, means nth disk from source to destination, and finally move the 2 disk which are already existing, means already we moved to the axillary. Okay, from there move it to the destination needle. These are all the 3 steps we are going to implement. Okay, now as a pseudocode, how to write it? See here, the general case here, move n minus 1 disk from source to axillary. Base case, moving the nth disk from source to destination, and again move n minus 1 disk from axillary to destination. Here, this Towers of Hanoi problem, it differs from our earlier simple problems. Okay, so in our previous problems, we have only base case and general case, and we are running the general case n times until we reach the base case. Okay, here general case, base case, and general case, we are using it alternatively. Okay, we are combining the general case 2 times here. Okay, now how to write algorithm for this Towers of Hanoi problem? For this problem, we need 4 parameters. What are the 4 parameters? Means the number of disks to be moved, the n value. Okay, whether we are going to move 1 disk or 2 disk or 3 disk or 4 disk, you can give the n value. Okay, the number of needles is always 3. Okay, now the n disk, when you're moving the nth disk, what is the source needle, and what is the destination needle, and what is the axillary needle? So we have names for all these 3 needles here, A, B, C. Okay, this is what the needle names. Okay, now the whatever the description given here, that as a pseudocode you can write it in the like the below one. Okay, call Towers of Hanoi n minus 1. Okay, totally move n minus 1 disk from source to axillary. Okay, use the destination needle as the axillary one. Okay, now move the nth disk from source to destination, and finally reversing the first step, that is move the n minus 1 disk from axillary to destination. Okay, and move the source needle as a axillary needle. Okay, so in the first step, the source is source and the destination is axillary. Okay, and the destination node we are using it as a axillary needle. Axillary is the destination, and the destination needle we are using it as a axillary. Okay, so this is pseudocode representation. Now let us see the algorithm. Okay, so this is the algorithm. Okay, algorithm Towers of Hanoi. So for this Towers of Hanoi, as we already discussed, there are 4 parameters: number of disk, source, destination, and axillary. Okay, first we are printing towers. Okay, so how many, what is means which disk we are going to, number of disk totally, and the source disk, and the destination disk, and axillary. For the current iteration, what are the values for this? okay, and if number of disk is 1, okay, move the disk from which source to which designation, the needle names we are printing. Else towers of move n minus 1, okay, n minus 1 disk from source to auxiliary, and then move nth disk to designation, and again move n minus 1 disk from auxiliary to designation, okay, recursively we are calling it. So this is the code, okay. So let us see the implementation. See here, if n equal to 1 means the nth disk, which step we are moving source to designation, okay. Else, okay, n minus 1 disk from source to auxiliary, and move nth disk, and n minus 1 disk from auxiliary to designation, a recursive call, okay. So let us run this program. Okay, so I'm giving the number of disk as a 1, okay. Directly move from A to C. If there is only one disk means source is A, designation is C. Directly we moved from A to C. That's it. Now let us check the second number of disk is 2. Okay, number of disk is 2. Totally 3 steps. Okay, in step 1, move the disk 1 from A to B, and in step 2, move disk 2 from A to C, and in step 3, move disk 1 from B to C. B is the auxiliary. Okay, now let us try it for 3 disk. See here, 3 disk means how many number of steps required? 2 power 3 minus 1. So 2 power 3 minus 1 means 8 minus 1, 7 steps. See here, 7 steps are there. First step, move disk 1 from A to C. You can compare this with the picture given in your text. Okay, so that I included in the slide also. Let us compare. Just wait a minute. Now, this is the output we are getting. See here, in step 1, okay, in step 1, move disk 1 from A to C, okay, move disk 1, the topmost disk, from A to C. So this is what step 1. Okay, now step 2, move disk 2 from A to B. See here, move disk 2. Okay, the second disk we are moving from A to B. Okay, and the third step is move disk 1 from C to B. Okay, we already have disk 1 in C. This we are moving to B. Okay, we moved to B. That is what step 3. And the step 4, it is moving the disk 3 from A to C. See here, moving the disk 3, the third disk, from A to C. Okay, the same result we are getting it here. Okay, so this is what the towers of Hanoi problem. Okay, suppose if you are willing to implement it using the iterative code, iterative algorithm, okay, it may be difficult. Okay, so difficult to implement the iterative algorithm for this problem. But recursive solution for this towers of Hanoi is very simple and easy to understand. Okay, the basic thing is before moving the nth disk from source to designation, move n minus 1 disk from source to auxiliary, then move the nth disk from source to destination, then move n minus 1 disk from auxiliary to designation. So these are all the three steps involved in Towers of Hanoi. Okay, so this is our third example. In recursion, the very first example that we discussed is a factorial problem. How to implement the factorial problem using recursion. Okay, then the second exercise that we discussed is a GCD, greatest common divisor. How to solve it using recursion. Okay, and the third algorithm we discussed is a Fibonacci series. How to print Fibonacci series using recursion. Okay, that Fibonacci series problem we discussed. And the fourth problem that we are discussing is a Towers of Hanoi. Okay, the introduction to Towers of Hanoi we discussed, and the algorithm we discussed. So this is what Towers of Hanoi problem. Okay, how to implement it using recursion. And the last one is a prefix to postfix conversion. Okay, so what is this prefix expression, postfix expression means? Whatever the arithmetic expression we are writing so far. Okay, so that expressions can be expressed in three methods, three formats. What are the three formats means? Infix expression, postfix expression, and prefix expression. Okay, so infix expression means the operator. Okay, if you take any expression in a mathematical expression, there will be operands and operators. Okay, in infix expression, operator will come between operands. Okay, in postfix expression, operator will come after the operands, and in prefix expression, the operator will come before operands. Okay, the example is given here. A plus B, if you are writing an expression A plus B, it is an infix expression. The same, if you wish to write it as a prefix, means you need to write it as a plus A B. Here A and B are operands and plus is the operator. The same, if you wish to write it in a postfix format, means A, B and plus. So the operator is coming at the end. Okay, so these are all the three different notations used to write any expression. So there are advantages of prefix expression and postfix expression. Okay, for our understanding purpose, okay, reading and writing the expressions in infix format is very easy. But when we use the expression in systems, computers, okay, so the compilers will store the expression in prefix format or postfix format, because compared to processing an infix expression, processing of a prefix expression is very easy. Okay, so we can avoid the parenthesis based on the operator precedency. Okay, so processing a prefix expression using computer is easy. That's why the infix expression, even though we are writing the infix expression in our programming languages, it will be converted and stored as a prefix expression or postfix expression. These are mostly used in your compiler engineering. Okay, so the compilers mostly it will store the expression in this format only. Okay, so that's why these different notations are available. Okay, now our aim here is how to convert given prefix expression into postfix expression using recursion. Okay, actually this program is a very means a little bit lengthy problem. Okay, so here we need to discuss about two algorithms. The first algorithm converts a prefix to postfix. For that, we need to find the minimum length of the operands, because an operand it is not always a single operand. Okay, so A plus B if you are taking means here A is operand. Sometimes the operand itself may be another expression. Okay, that is a D into C plus A. Here D into C is a one operand. Once it is evaluated, then it must be added with the C. Okay, so we need to find the minimum length of the operand. Okay, and after that we need to find the entire expression length. Then we need to perform the conversion operation. So here, to find the length of an expression, we will use one more algorithm. Totally two algorithms we will use in this problem. In the prefix to postfix conversion, using recursion. Okay, so that problem we will see it in the next class. Okay, next class we will see this prefix to postfix conversion and also how to trace the recursive algorithms. Okay, suppose if any question is given to you, what is the output of this function after calling with value 5? Okay, recursive function code is given to you, and if some question is asked means how to trace it. That example also we will discuss it in the next class. Okay, if you have any doubt in today's session, please post it in the chat window.
Sir?
Yeah, Arjun, very good question. Prefix to infix and postfix conversion, we can do it easily in stack. Okay, so that again we are going to implement in our second unit. In second unit, we will study about the concept of stack. That time again we will use the stack for this conversion process. Okay, here in first unit we are studying about recursion. So using recursion, how to solve it, that we are studying it here. I'm not saying that using recursion is the best way. Okay, so using recursion, how to solve it, that we are going to study it here. Again, we will do the conversion operation in the second unit also. Actually, in Aditya, in infix we will use the braces, and in prefix to postfix we will remove the braces. Okay, if no doubts, we can end the session. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.